Alright, back in CCNA1, Chapter 6, the network layer. My favorite layer, your favorite layer, everybody's favorite layer, the network layer. Pretty big chapter. A lot of confusing stuff. Remember, this is just review. You have 4 more classes where you're actually going to program the stuff that these are talking about. So you just want to get the concepts as much as you can so that you can learn more about them as we go along. This is all a building block for another building block. Yeah, it's big concepts, a lot of theory. So anyways, describe the purpose of the network layer in data communication. Explain why IP version 4 protocol requires other layers to provide reliability. Explain the role of major header fields in IP version 4 and IP version 6 packets. Explain how host devices use routing tables to direct packets to itself, a local destination, or a default gateway. Compare a hosting table to a routing table in a router. Describe the common components and interfaces of a router. Describe the boot up process of a Cisco IOS router. Configure initial settings on a Cisco IOS router. Configure 2 active interfaces on a Cisco IOS router. And configure a default gateway on network devices. So actually we're getting to some fun stuff. We'll have a packet tracer coming up where you're actually going to use some commands. We will do some small configuration coming up, but not too much. So I'll get my friend packet tracer out. Hopefully you have yours. Alright, so on the network layer, we definitely, what's happening at the network layer? Well, definitely addressing. I've talked about IP version 4 addresses already, IP version 6. We're going to do more encapsulation because we encapsulated every layer, as we remember from the first review table. And then our most important is probably routing. We have a little bit of de-encapsulation as well because we are encapsulating. So, addressing. What is the addressing going on here? In the same way that a phone has a unique telephone number, end devices must be configured with a unique IP address for identification on a network. An end device with a configured IP address is referred to as a host. Okay, so this goes back to, so remember this address that we're talking about, this network one, this is going to be like your house address. I don't like the telephone number as much as a house address. And then the MAC address was the name. So we're doing where it's going. Okay, so where are we going to send that box? And then the layer 2 is the person that opens up the box, right? The rest of it is either what's in the box or the box itself. So that's my scheme on encapsulation. So the network layer receives a protocol data unit (PDU) from the transport layer in a process called encapsulation. The network layer adds IP header information such as the IP address of the source, the sending, and the destination, the receiving host. After header information is added to the PDU, the PDU is called a packet. So if we look at how we're sending this, right, what it's saying is all of this stuff above us is put into our packet. This is a packet. And so then it's broke down in frames, which is then broke down to bits and reassembled as it goes along. Then we have routing. So what is routing? Well, it's what routers do, and routers route. But what does that actually mean? They pick the best path to a network. So routing protocols do 2 things. They pick the best path, the fastest path, and then they also do this other thing called they stop loops, because if we had a routing loop, then we'd just be wasting all of our bandwidth. So routing. The network layer provides services to direct packets to a destination host on another network. To travel to other networks, the packet must be processed by a router. The role of a router is to select paths for and direct packets towards the destination host in a process known as routing. A packet may cross many intermediary devices before reaching the destination host. Each route the packet takes to reach the destination host is called a hop. De-encapsulation. When the packet arrives at the network layer of the destination host, the host checks the IP address of the packet. The destination IP address within the header matches its own IP address. The IP header is removed from the packet. This process of removing headers from lower layers is known as de-encapsulation. After the packet is de-encapsulated by the network layer, the resulting layer 4 PDU is passed up to the appropriate service at the transport layer. Alright, so we have typically, we're going to say, we can kind of talk about these other ones. I think they did on that review. But anyways, our base are IP version 6 and IP version 4. And what came before them are these legacy IPX, AppleTalk, and whatever this connectionless network service is, DECnet. Okay. These two, Novell invented, Apple proprietary. And the problem with these legacy ones, right, is everybody was developing their own networking thing, so we went to this whole open model, and that's what the TCP/IP model is, right? Promotes competition and all kinds of good stuff. Alright, so characteristics of IP. Connectionless. No network connection is with the destination established before sending data packets. So what that means is it's like a circuit at this point, right? So we have our host over here and our host over there. It doesn't do like a 56K dial-up, and establish the connection before it sends it. It just assumes it's going to get there and sends it along the path, right? Best effort. Unreliable. Packet delivery is not guaranteed. Well, it kind of has to do with what we just talked about. It just sends it. And so it's either going to get there or not. All this router knows is it thinks the route is this way. And so it will send that packet along. It's media independent. Operation is independent of medium carrying the data. What that means is TCP/IP or IP doesn't care, what media. It doesn't have to stay on the same media. But we already know that because we have we know that we can use wireless, which uses a different frame and media than, say, Ethernet. So, and Ethernet can use different media as well. So here's our connection list. It's the same thing. If it was connection oriented, which some of the top layer, one of our transport layer ones is actually, it's called TCP, which is how we get our name. But right, as I said, if we formed a connection, we would know, like before we sent the packet, it would establish a connection to guarantee that the destination is where we think it is. That's not how any of this works. So it just sends it unless the upper layer protocols tell it differently. So the sender doesn't know if the receiver is present, if the letter arrived, if the receiver can read the letter, or when it is coming. It just sends it along its way. And that is connectionless communication. So best effort or unreliable. And all this means is best effort or unreliable means that after we send our packet over here, we are not told by this computer, it doesn't send back and say, hey, I got it, right? So we just roll the dice and we don't know where they land. Media independent. Alright, so what it's showing here is serial uses a different layer 2 encapsulation than, say, this Ethernet, and this optical fiber can use a couple different. It could use Ethernet or it could use other encapsulation. Back to Ethernet, then we're at 802.11 before we get there. So we can use just because of the data link layer, we don't have to worry about different medias, right? We know the MAC address layer, or the MAC layer, sublayer of the data link layer, allows us to use any kind of media. So here is what we're receiving. Okay, the transport layer, it has all this application, it has the port numbers and that kind of thing in it. We'll study that when we get the transport layer. And then it has the data, and the data is the rest of the payload of the application layer and up. And so to make a packet, we put an IP header on there, and so IP header encapsulated with the transport layer PDU is called a packet. So the network layer adds a header so packets can be routed through complex networks and reach their destination in TCP/IP based networks. The network layer PDU is the IP packet. So I guarantee you'll get that on the test. Make sure you know that the network PDU is packet, transport PDU is segment, and the data link layer PDU is frame, and physical is bits. Okay, so now we have two types of IP headers, right? We have IP version 4 header and IP version 6, and it has a lot of junk in here. And we'll read over it. So the header, so what we're looking at when we're talking about the header is this thing right here, right? So what we're encapsulating the segment with. And so the segment right here is just called the payload when we go to this next part. And all that, and that's what it says right here. We have the IP version 4, which identifies the packet characteristics, and then the payload, and those two things together make a packet. So the first thing we have is the version, and the version is going to tell us whether we're using an IP version 4 packet or an IP version 6. And the reason that's important is because when we study these packets, they're going to be different. And then we have the DS, or the differentiated services, formerly called the type of service field. The DS field is an 8-bit field used to determine the priority of each packet. The first 6 bits identify the DS code points value that is used by a quality of service mechanism. The layer 2 bits identify the explicit congestion notification value that can be used to prevent drop packets during times of network congestion. Okay, so what this is we're just going to say DS is QoS, alright, quality of service. And we can do QoS, this is DOS, QoS at either the DS, or at layer 3, or at layer 2. Remember we saw that slide for a second in the data link where we could do QoS there. So there's a few areas we can do QoS, and this is one of them. This would be telling routers, hey, it's congested, drop packets that don't matter, and send these ones because they're very important. Time to live. And so this is a hop count, basically. It contains an 8-bit binary value that is used to limit the lifetime of a packet. It is specified in seconds, but is commonly referred to as a hop count. The packet sender sets the initial time to live value, and it is decreased by 1 each time the packet is processed by a router or a hop. If the TTL field decrements to 0, the router discards the packet and sends an ICMP time exceeded message to the source IP address. The traceroute command uses this field to identify the router's use between the source and destination. Protocol. This is an 8-bit binary value indicated by the data payload type that the packet is carrying, which enables network layer to pass the data to the appropriate upper layer protocols. Common values include ICMP, TCP, and UDP, which we'll learn more about those when we study the transport layer. Alright, source IP address. Well, this is where the packet is coming from. Contains a 32-bit binary value that represents the source IP address of the packet. Destination contains a 32-bit binary value that represents the destination IP address of the packet. Okay, so this destination is the most important when we're routing. This is what routers use to say, do I know where this is? Because this is where they're sending it. This is all they look at. The source is a little different. Source, if we're doing network address translation to the internet, this source actually changes, but we're not going to go there yet because Actually, these logical addresses, what we're going to say as we're routed, logical addresses stay the same. Remember, every hop, our MAC addresses change, but the IP addresses stay the same because we need to know what network we're going to get to. So from here to here, our layer 2 addresses are going to change. Here, we're going to change the source and destination. Here, we're going to change the source and destination. Here, we're going to change the source and destination. But our IP addresses stay the same. It's going to say this is the source, this computer is the source, and this computer is the destination. And that stays the same throughout routing, and that's what the routers are looking at to get it where it needs to go. Alright, so now we have header fields. The internet header. Alright, the remaining fields are used to identify and validate the packet or to reorder a fragmented packet. Internet header length contains a 4-bit value identifying the number of 32-bit words in the header. The IHL value varies due to the options and padding fields. The minimum value for this field is 5, i.e. 5 times 32, 168 bits, or 20 bytes, and the maximum value is 15. Yeah, I don't even know what to tell you about that. So I don't know where this would ever be important to you. Maybe if you became a programmer. Anyways, what it's going to do is it actually tells it how, I don't know, it's going to move based on the data. So it's going to offset if you have more data or less data. It's basically just telling you how big the packet is. Total length, sometimes referred to as packet length. This is the 16-bit field that defines the entire packet fragment size, including header and data in bytes. The minimum length of the packet is 20 bytes, plus 0 bytes. Alright, the maximum is 6,535. Once again, has to do with length, okay, or size of the header. Header checksum. This 16-bit field is used for error checking of the IP header. The checksum of the header is recalculated and compared to the value in the checksum field. If the values do not match, the packet is discarded. Alright, so now a router may have to fragment a packet when forwarding it from one medium to another that has a smaller MTU. That's maximum transition unit. So if you're going to different medias, this could happen. When this happens, fragmentation occurs, and IP version 4 packets uses the following fields to keep track of the fragments. Identification. This is a 16-bit field uniquely identifies the fragment of the original IP packet. Flags. This 3-bit field identifies how the packet is fragmented. It is used with the fragment offset and identification fields to help reconstruct the fragment into the original packet. Fragment offset. This 13-bit field identifies the order in which to place the packet fragment in the reconstruction of the original unfragmented packet. And so all it's saying is these are used. Basically, we kind of talked about buffering. It's basically the same thing. We just break down the size of the packet. Instead of it flying all in one piece, it comes across in several pieces and is put back together. Sample IP version 4 header. Okay, if you guys want to do this, you can look at these pictures, but I actually encourage you to download Wireshark and actually look at the IP header of a web page as you're doing this. So how Wireshark works is just pulled this thing up here, and so we go to our interface list. I have a lot of adapters, so we just find the one that we need. I believe it's this one. That's the only one receiving packets. Come on. Alright, so we're just gonna try it from here. And we start it. Alright, and we have this stuff going, and let's wait for some TCP there, so we stopped it. Alright, so because I have Net Academy open, all kinds of stuff's going on. So if we want to find some HTTPS, here we go. So in Wireshark, we have the frames, right? This is the frame on the wire. Why is it not expanding? It should expand. So we can, this is the MAC address. This is our layer 2 information. Then here's our layer 4. So it's showing us the frame in the packet. But anyways, this is your real life header. So just go to any website, record, then click stop, and you can open up the Wireshark, and in this screen down here, right, it's going to show you what's actually in the header, right? It shows you your header length, DS, all the stuff we're talking about. This is real life TCP/IP model. Alright, so even though IP version 4 is great and we still use it, the problem with IP version 4 is IP address depletion. When it was created, nobody really thought this whole networking thing was going to take off like it did, right? When this was built, it was made for colleges, you know, to study, I think, like atom math equations together, right? Like they could share information. And then it took off, and it's made a lot of changes from them. But the problem is, IP version 4 only has 4 billion IP version public addresses, right? And so we have to come up with a solution. Supposedly they're all gone. You can still pay enough money and get one. Internet routing table expansion. A routing table is used for routers, make best determinations. IP version 4 routes, they're not as efficient as IP version 6, is basically all this means. And lack of end-to-end connectivity. Cisco sells, you know, the Internet of Everything, where we're going to put, you know, wireless devices in trees to track how they grow, and every cell phone, every person. And so with our 4 billion, we just don't have enough addresses to do that. So we came up with this. This one undecillion addresses IP version 6, which is a lot. It's comparable to grains of sand in the Sahara Desert. That's how many addresses we have. So what does IP version 6 allow? Increased address space. Why? IP version 4 has a maximum of 32-bit addresses. This has 128-bit addresses. Improved packet handling. The IP version 6 header has been simplified with fewer fields. This improves packet handling by intermediate routers, and also provides support for extensions and options for increased scalability and longevity. It eliminates the need for NAT. So NAT was where we change our IP address because we don't have enough when we go on the internet, and it's also a security measure. But anyways, we have so many addresses. If we wanted to, we could put public IP version 6 address on every device, right? And integrated security. IP version 6 natively supports authentication and privacy capabilities, known as IPsec. With IP version 4, additional features had to be implemented to do this. So just IP version 6 just sounds great, right? Well, you'll probably get pretty good at IP version 4 and decide that IP version 6 isn't as cool as it seems. So so we have our IP version 4 header. Now we have our IP version 6. And as you can see, IP version 6, much simpler. We had all these little tiny fields in here on this one, flags and everything else. This one, you know, we basically have, what do we have? 1, 2, 3, 4, 5, 6, 7, 8 fields. So makes it more efficient. No requirement for processing checksums, simplified, more efficient. La-di-do. So let's actually check out what we have here in the great IP version 6. So we have version, right? Well, we still have to tell it we're version 6, just like the last one. Now we have traffic class, which is different than the DS, right? It does the same thing. It's the QoS, right? Traffic class. We're classifying how important our traffic is, so that's how you remember that. Flow label. This 20-bit label provides a special service for real-time applications. It can be used to inform routers and switches to maintain the same path for packet flow so that packets are not reordered, right? So instead of fragmenting them, it says, hey, I got 6 more behind me, right? Payload length, that's not exactly how it does it, but this 16-bit field is equivalent to the total length field in the IP version 4. It defines the entire fragment size, including header and optional extensions. Next header, this is equivalent to the IP version 4 protocol field and indicates the data payload type that the packet is carrying, enabling the network layer to pass the data to the appropriate upper layer protocols. This field is also used if there are optional extension headers added to the IP version 6 packet. Hop limit. This 8-bit field replaces the IP version 4 time to live field. This value, which remember is considered a hop count, this value is determined by one router that forwards the packet. When the counter reaches 0, you get an ICMP version 6 message that did not make it to its destination. Then we have our source and destination IP version 6 addresses. What's the difference? They have 128-bit field identifiers instead of a 32. And we could do, if you're interested in seeing this header, we could set up IP version 6 in class so you can see that header and the differences. Alright, so host forwarding's decisions. So this is the basics of routers. So how do routers work? Well, the first way a router learns routes is itself, right? So this is the most primary. And so what we do is we program this interface and then we program this interface, and they have to be different networks because that's how routers work. And so it knows whatever subnet this is, and the subnet actually tells it the size of the network. So then it says, alright, so if this is this interface, then I know this network is here because you programmed me for that, and this network's here because you programmed me for that. And they're saying that this is a remote host, but it's only remote to this network. And so, but what they're telling, actually I went too far, sorry, this is talking about something else. So first, if we want to test an IP stack, you can test yourself, and that's through what's called the loopback, right? And that's 127.0.0.1, and we'll actually learn that, actually if you look right here, any IP within the network of 127.0.0/8 refers to the local host. So if we try to ping that, if I bring up my command prompt here, man, my computer does not want to cooperate today, does it? So if I bring up this header and I go command prompt and I say ping 127.0.0.1 or 2 or whatever, I put 172. Okay, so ping 127.0.0.1, and I get a ping back. And what I'm testing to see if the TCP/IP stack is loaded on my computer. If I can't ping myself, I can't ping anyone else, and I can't get connected to anyone else. So that's what that's testing. So the next thing I'm testing is what I'm programmed for. Alright, so if I want to see, if I'm having network connectivity problems and I want to see why, once again I can go back to my command prompt and I'm once again going to test myself. I don't know what my IP address is right now, so we'll config it. 192.168.0.12, so I can ping 192.168.0.12. I've tested the loopback. Now I want to make sure that the address that I think I'm programmed as works, and it does. Okay, so Next, if I want to get to a remote host, I'm going to go to a place called a default gateway. And we can find the default gateway once again, if my computer will work with me here. We go to our network settings where we would statically set a network, right? Adapter settings, properties, then IP version 4 properties. And as you can see right here, we have a default gateway. And what the default gateway is the way to a remote network, right? Or if you're not in my local network, right? So my local network, I don't need a router, right? It's just a switch, and I can go to this local host, or if there's another local host up here, I can go there. But then let's say I want to go to a different network. That means I'm going to a remote host. And so I send it to my default gateway, which is the definition of a default gateway. The simplest is the exit out of your network. So if something's not in your network, you're going to send it to your default gateway, and hopefully the router finds it. And that brings us up to default gateway. Alright, so these are some terms that you're going to see again when you're in CCNA 2 and about this chapter in CCNA 2. So this is what I was talking about, the router. We have the directly connected routes, which are automatically put in. What is it talking about here? Alright, never mind, it's not talking about how the router learns these routes yet. What it's talking about is, we can see, remember your computer is also a layer 3 device, so if you want to see what it's talking about, you say route print. And so what route print does is it's showing us, it'll show us that 127. It shows us our local, right, our direct connection, which is the 127, which is right there, and then it'll show us local network route, which is we're on the 192.168 here, so 192.168.0 is right here, and then the local default route, how to get to my default gateway, and my default gateway I believe is 0.12, and so that's what it's showing us. And so that's on a router. It'll be a little different on a router than a computer. But if you guys want to see what they're talking about here, that's what you do. Route print. IP version 4 host table. Here's our route print. You could also do netstat-r. Shows the same table, right? And if we want to see this on a router, this routing table is through show IP route is the command we would type, but that's for a different time. Okay, so this is just talking about the routing table, and basically it's saying this 0.0.0 is our default route, which means it's going to be sending it to our default gateway. And so it says if it's not matching anything else, send it to this 0.0.0 route. This 127 that we're seeing, we know that already as our loopback, testing our IP stack. Then this 192.168, if that was our network, this would be our local network, saying, hey, this is, we can ping anybody inside from, we can ping any host from 10.0 to 10.255. Then this 224 is what's called a multicast. Maybe you remember a multicast from last chapter where it was sending one-to-many, and so it has that registered. This last one is a broadcast, which remember we had that on the layer 2 as well, where it just sends it to everyone inside the network. So everyone inside this router interface, this is where the network stops, that router interface. The default gateway is where the network stops, and so it's going to broadcast to anybody, such as this really awesome computer that I drew right here. It would all be broadcast within there. So that's what's going on inside of there. So sample IP version 4 host routing table. Well, I already showed you one. Go ahead and do a netstat-r or a route print, and it will show you your own. Take a look at that. IP version 6, it's probably in there too. close that window. But you can look at that. We're not going to hit this too hard until we actually come to IP version 6 addressing. So let's learn the IP version 4 first. So here is finally what I've been ranting about, how a router learns routes. So the first way is by being programmed to on an interface, and it says these are directly connected routes. So this R1 knows these directly connected routes. The remote routes we have to program through a routing protocol or manually through a static route, and these are the remote routes. And so notice that we're connected to the networks of all these. These are all router interfaces that are directly connected, so we know all of those. So what it's doing right here is it's showing you an example of routing tables. Go ahead and take a look at that. The D's are EIGRP, the C's mean connected, and then the local is just this special one. It's basically on the newer routers. On the older routers you would not see the local, but the local means that our router is actually programmed for that IP address, and so that's what they mean. The C's are directly connected. And here's that talking about that. C identifies a directly connected network. Directly connected networks are automatically created when an interface is configured with an IP address and activated. Local identifies that this is a link local route. Link local routes are automatically created when an interface is configured with an IP address. Alright. So the destination networks, when we on this, if we were just to program IP addresses of a router, we could only go to this network, and this network. If we tried to go to these remote routes, it would fail without us using a static route or a routing protocol. So that's what they're talking about here. S identifies the route was manually created by an administrator, known as a static route, right? D identifies that a route was learned dynamically from another router using enhanced interior gateway protocol EIGRP, which is a dynamic routing protocol, or there's OSPF, which is identified with the O, which it's learned dynamically from OSPF. So open shortest path first. Alright, so they're showing us this routing table entry. So what we're seeing right here is we did a show IP route on this router, and this was programmed in. It shows us this D. Okay, so the D means that's our EIGRP, so route source. How we learned it is this first thing. Then this next one is the destination network, right? Because that's what these routers care about, is the destination router. It says how we're going to get there. I learned to get to 10.1.1.0 through EIGRP is what it's saying. Then it says my administrative distance or trust in this route is 90. So if there was another route to the same network, say it was a static route and had an administrative distance lower than this, it would take this route out of the table and put that one in. And then this one is a metric, and so depending on what routing protocol you're using, the metric's different. EIGRP uses bandwidth and distance by default. OSPF uses distance, and static routes, they just trust you. So it's just a default metric. Then this via tells us how we're going to get there, our next hop. And so when we make a remote route, it's right here. We're putting where is the last point the router knows by directly connected routers to get to remote networks, such as these over here. And so that last place we know is the serial link on .2, it must be 226, so that was a 9. Anyways, and then the other is the interface that's sending it out. This is serial 000, so that's our last thing on there, and that's what it's telling us. It's talking more about that next hop address. Make sure you read through this, but pretty much summarized it there. this is our routing table, much like our routing table from print route. This is just a show IP route inside of a router, and it shows all of our directly connected routes, or all the routers we know. Alright, so we're just going to jump straight into a router, because pretty soon I will show you for Packet Tracer how we're going to do that. Alright, so there's different types of routers. We have branch, WAN, and service provider. Basically, most of the routers we're going to be using are branch routers, because these WAN and service provider routers are much more expensive. We do have 6500 switches, but we do not have the Cisco aggregation service router, right? So what this is doing is it's connecting you to WAN technologies such as ATM and MPLS or something like that. And this would be what probably an ISP would have running. Then we have service providers, definitely ISPs, and so very expensive. 7600 series routers. We have 2900, so that's 29 and 2800 branch routers in the classroom, and you have all kinds of routers in the Packet Tracer. So regardless of what a router is, they all have the same thing. They're a computer. Just like our computer could be programmed to be just a router, they've been designed to just route, and they have some special stuff, but mostly they have the same components as your computer. They have an operating system, they have a CPU, they have RAM, and they have a ROM. Alright, so all things that our computers have. They do have a special thing called an NVRAM. And so the router CPU, so this is what's going to process and do all of the routing, right? It does all the functions for the OS, all the calculations. The router memory, okay, so we have a lot of different types of memory. So we have RAM, which is volatile, and in this volatile RAM, just like in a switch, except we're storing some different things, we have the running copy of the operating system, just like Windows is running the copy of Windows in your RAM. Then we have the running configuration file, so what we've configured the device to do, but in the IP routing table, ARP table's packet buffer. Okay, so if this stuff isn't saved, it's lost forever. That's why we have this thing down here, the flash, which works as our hard drive. And if you look at the flash, it has the iOS, that's our saved copy of the iOS, and other file systems. Then we have the NVRAM, the non-volatile RAM, and what's in there, our startup configuration. So at startup, we get the iOS and put it in the RAM from the flash, and then we take the startup config from this other file, the NVRAM, this other storage, and put it into the running configuration. And then the ARP and packet buffers do themselves while they are, depending on if we have static routes stored or whatever's going on, but they learn as they go, and the packet buffers, build as we send data across. Then we have the ROM, and so the ROM is this thing just like on your computer. It does the boot up instructions, the basic diagnostics, all known as post, and then if something's wrong, it gives us a limited iOS. If it can't find this iOS in the flash, it gives us a way to load it in there. And if we do a password reset, that is what our where it's running from is the ROM. It's called ROM-on in the ROMMON, ROM-on, most basic operating system for one of these devices. So feel free to look through here and look at all these devices. So the back of the router, it has some stuff that we don't have on a switch, right? We have the console, which we had on the switch, but it has this aux port, and we've talked about this aux port. I think it's the emergency, right? And then we have the LAN interfaces, which are similar to switch ports, right? But then we have these WAN interfaces and flash cards, which we don't have on a switch. And so what these allow us to do is stuff like serial or advanced WAN connections that switches are a LAN device, so they don't have those. connecting to our router. So we have in-band and out-of-band management. In-band management means we're in our network, so we would come in, we'd telnet or SSH through our LAN interfaces, through either one of these. Either they are fast Ethernet 01 and 00, or fast gigabit 01 and 00. Then we have our aux port and our console cable, and both of those, one's through cable and one's through a dial-in 56K modem, something like that. And so those are out-of-band management. And what out-of-band management is doing is it just means we're not going through an Ethernet network. So remember, in-band means we're in our network, we have an IP address, we're using telnet or SSH, something that requires an IP address, whereas out-of-band we go through different software such as Serial or Modem Emergency. So that's what this is talking about right there. If what I said didn't make sense, feel free to read about those LAN and WAN interfaces, or the telnet and SSH. Alright, so now we have the router boot up, and what's going on with routing. What do routers do? Or what does the Cisco IOS allow us to do as it gets booted up? It provides the addressing, tells us about our interfaces, and sets them up. It does the routing. It provides security, QoS, or resource management. So it's all being programmed through the Cisco IOS. So, as I said before, how it boots up is we take from Flash, we take the Cisco IOS. And, it's going to give us all of our functions of our operating system. It's just like Windows booting. Then it's going to load our saved configuration, so our startup configuration, which is like your saved Windows user files. It loads up your desktop how you like it. And so this loads up the startup and puts in all of our programming if we were to have a power outage, right? Otherwise that's sitting in RAM and running, and if power went off we would have to reprogram everything. Okay, router boot up process. So first thing it does is the post. Okay, so first is post, which is it's checking to make sure our RAM and everything's hunky-dory. Then it goes to the bootstrap. Okay, so it loads the bootstrap, which then tells it where to find the iOS. So then the bootstrap loads the iOS, and then finally we load the configuration file. Alright, and we do have some options. If you look over here, we can load the iOS from Flash or from TFTP server. We can load the configuration from the saved NVRAM, from a server, TFTP server, which is just a server that would load that configuration, or we can program it through the console and it can load it through the console. Alright, so we have this show version command, and there is a test question about this, so make sure you look at where this shows the memory that's being used and that kind of jazz. But show version is a command that shows us our iOS version, software and RAM that is being used by the router. Let's see if we can see that up here. No, it's just the software and the RAM. It shows us where we loaded it, what it's called, so the location of the iOS, what CPU and the amount of RAM we have. That's right in here, right? This is our memory. Let's see. Then we have that shows us our NVRAM and our Flash. Right? So there is a test question where it asks you if you have enough RAM and Flash to do it. So make sure you know where to find it. Alright, we're finally getting into router configuration. So pull up my packet tracer here. Have a real fine packet tracer doing here. Notice I use straight through cables because they're devices. Layer 3 device, layer 2 device, layer 3 device. So we need cables, straight through cables. We'll talk about why when we get to it in the chapter. And you notice we have double red lights. It's because routers are off by default. And so this would be just like us consoling in. We say no. We always say no whenever we see that configuration dialog. You're taking this class so you don't have to use easy mode, and this gives you way more features. Okay, so first thing we do when we get into this router is we go into privileges exec, and maybe you remember we click enable to do that. And then we want to secure this thing. So we say configure terminal, right? Because we want to go into global configuration. And so now I want to password it, so I say enable secret, not enable password because that's legacy, and we say enable secret, I don't know, password 01. There we go. So we have password 01. Don't ever use that in a real environment. What else do we need to know here? Oh, okay, so if we wanted to go into our lines, maybe, I think I did this with you guys, so we say line. If we wanted to see everything, we just have, alright, show, run. And that show run goes through here, and we can just press the space bar. I have line console 0, so that's a password for my console. I could console my auxiliary if I wanted to. And I have line v2i 0 through 4. So I say config t. I'm going to actually put a host name on here. Host name router 1. Okay, so as you can see, that changed my name right here. That's how I uniquely identify my router. Then I can say line v2i 0 space 4. This is what, after I get an IP address, would allow me to telnet. And I'm going to say password 01 and log in. Even though I can see that it's already in there, it's just a good habit to get into. Then I'm going to say line con 0 password 01, and this is meaning that my password is going to be password 01 when I console in. Alright, so whatever you put after the word password is what it's going to be. And then I'm going to type login again just in case. So then I can go back out and do, I'm going to do one more thing. Actually, no, I'm going to show run again. If I go all the way down here to the show run, maybe you guys can see this. My passwords are in clear text right here, not the secret, because the enable secret encrypts it. But my passwords at the bottom of the console and line are not, and so I'm going to say config t service password encryption. So now they're going to be encrypted. Show run. That just does a real simple MD5 encryption, and so now they're a bunch of numbers and letters. Then our most important thing, if we do something like that, copy, run, start. Alright. Copy it asks destination file name, startup config. You just press enter because that's where you want it saved, so it'll load it. Next, configure interfaces. So we go to our interfaces. So we look back over here, and so there's a couple ways. You could just hang your mouse over the G0 interface, and it would tell us that. I like to do it fast, so I just unplug it there, and it tells me I need to configure G01. So how I do that, I go back into configure terminal, interface G00, I say IP address, and whatever IP address you want to assign. That'd be, I'm going to say 192.168.1.0.255.255.255.0, which is actually the first host address for the network 192.168.1.0, and then I say no shutdown, which turns this interface on. And so now if we look back at our packet tracer, that port is started up. One side's green, one side's orange. Pretty soon both sides will be green. So we say show IP route, and this is that route I've been talking about. And as you can see, it shows us the connected route, which is 192.168.1.0/24, which just means 255.255.255.0. Means your subnet mask has 24 1 bits in it. Don't worry about that too much because we're going to spend quite a bit of time on subnetting, and it will be there anyhow. So yeah, don't stress out about that. Anyway, so we're going to keep going. We have that router programmed. Okay, so that's how we program one interface. Oh, and also A command that is very good for documentation, which you always want to document as best as you can so you don't get confused, is I will go back into interface G00 and I'm going to say description, and this is just going to tell me if I ever look at my running config where that actually goes, and I'm going to say interface to LAN 1, to local area network 1. Okay, so if I had another network off this router, I would call it LAN 2. So that's how we configure an interface. Now, there could be a lot of different interfaces. We have serial interfaces, gigabit interfaces. I don't know if I ever showed you guys this, but if we wanted to put in, first we want to make sure we save. So remember, we go exit, exit, copy, run, running config, startup config, tell it yeah. And so now we're going to go back out to this physical picture. I can turn this off, and if I wanted to put a serial connection on, I would go to an H2T for T1, and actually it has just high-speed serial ports. Those actually could be T3s. So if I try to go back in there, it won't let me. But if I start that up, as soon as it starts up, you'll see that I can plug in serial interfaces to it. So if you want to try it through serial interfaces, but you'll need another router, as a serial interface is a WAN connection. Here we go. We're started up, and so password 01 was my console password, enable. Password 01 was my enable secret password, and then I do a show run. And show run is going to show now that I have, before I just had gigabit interfaces, now I have serial interfaces. And notice that this tells you everything you did. So I have a description on there, I have an IP address, duplex auto. I didn't do those are default. And we can look at the other one. It says no IP address, and right there it says shutdown. If you're having problems, make sure you always issue a no shutdown. If you're seeing red, you want to see green, like so, or you probably have a problem with your router. And usually it is that you did not turn on that interface. Now the switch ports are turned on by automatically, so you don't have to worry about that. So that's our basic interface commands. Now, if we wanted to verify interface connections, we do show IP route, show interfaces, show IP interface. That's pretty much the gist of it. Now, stop saying now. Okay, so here we are. We're configuring a default gateway. So a default gateway, if we look at it's always going to be a router interface. All right, so it's how this computer gets out of its network. So it gets out through the router. So it's going to be right in here. That's my default gateway on there. And so on our PC, I showed you how to do that. And then on a switch, what the default gateway is, remember switches are just layer 2, so they forward frames. But if we want to telnet to these things, we can do configure terminal, and the command for a default gateway in them is IP default gateway, and then I put 192.168.1.1. Why would I put that? Hopefully you said because that is what I programmed for that interface on the router, and that's how that device would get out of there. You will be using these commands. So then, so what if I want to test all this stuff? So I'm going to go into my computer, maybe on Packet Tracer. Perhaps you've not messed around here. So you go into desktop, IP configuration, and I want to put it in the same network. So I say 192.168.1.2, 1.1.1. Remember, these IP addresses have to be unique, and I already use 1.1 for my default gateway, which tells me what to put in as my default gateway. So I have 1.1. I only have 2 devices in here, but I can test my connectivity by saying ping 192.168.1.1. I could ping myself as a loopback, but I already know I can ping outside of myself, so I know this is going to be successful. Or I could ping myself through 192.168.1.2, right, which is the IP address I assign. So if you're having problems with any of these, make sure you try pinging your loopback and yourself. Make sure you've turned on your interfaces and that kind of thing. These are all troubleshooting mechanisms, and they will come in handy for the activity that is coming up, the Packet Tracer assignment. You might want to actually throw this together, put some switches on the other side, and try to ping all the way through. If you put switches on the other side, This network will be 192.168.1.0, 255.255.255.0, and so the next network actually starts at 192.168.2.0, 255.255.255.0. So you can put the 1, 2, use the 1 and 2 on the next network, and make them ping. You just change the 1 to a 2 on these addresses I put in there, and you actually could program that SVI. If you remember how to set up that SVI, you could program that on this switch, and actually I'll just show you how to do it right now. So we have our switch right here. We say interface VLAN 1, and we say IP address 192.168.1.1. No, we don't, right? Because we already used that and they have to be unique. So we say 192.168.1.3, 255.255.255.0. Exit, ping 192.168 1.3. So what did I forget? So if I ever had this problem like this, I could go to a show run. And the thing is virtual interfaces are shut down by default, just like router interfaces. So we say config t interface VLAN 1 and no shutdown. Alright, so now if I enabled the VTY the same I did in the router, put a password on it, I would actually be able to telnet in. If you want to see how to telnet, I can't SSH yet. It'll use a few more advanced commands that we haven't got to yet, but if I want to telnet to my router, here I go. Telnet to my router, password 01 because I put it on that VTY line. Then enable, password 01 because that's the secret password. Okay, so hopefully that entertains you. You've learned some stuff. If you have any questions, would like an explanation on the packet tracer, like doing packet tracer with another switch and another PC, I'll show you what it would look like. Hopefully you figured it out. But here's a 2960. We're just going to take this connection right here, plug in the gigabit, plug it into there. Then we're going to take a computer, throw it out there, and plug in. Where's our straight through? Do I have my straight through? Is that what's going on? Yep, I do. So plug that in, and so all we'd have to do to get this working in the bare minimum, but I would use all the commands we've learned so far on both devices. Config T, interface G01, IP address 192.168.2.1, 255.255.255.0, no shut, and then a exit, copy run, start, or copy running config, startup config, save that. Then we go over here to our desktop, program in 192.168.2.2, 255.255, 192.168.2.1. Now this IP address on your default gateway, it could be anything. It's just whatever you program, any usable host address program for this default gateway. So now we could test this, and so we could ping 192.168.2.1, and we can ping that. So let's see if we can ping the other side of that router, which is 1.1. Okay, we can. And so now let's ping 192.168.1.2, which is the other computer. So what we've proved, what this has shown us actually, is that we have connectivity all the way over to here. Okay, and so this is basically what you're going to do, except you have to put in all your commands that you would put in, that we've learned so far for the packet tracer coming up. So anyways, good luck, and send me any questions or post it on the discussion board.